I know. I don't think she doesn't have to. He's going to send him. Because he knows this.
Today is 11/11. It's pretty cool. Say again. Oh, yeah, right. I think we all need to pause at 11/11 today to make a wish at 11/11 on the date 11/11. Oh, so I'm going to try to teach this a different way. I've been teaching this particular lesson for a really long time, but I've decided that I'm going to try a different approach. This section has caused a lot of grades to drop in the past, so I'm going to take a different approach. It's the old your horse dies, you got to get a new horse kind of thing. So I'm going to try to teach this a little bit of a different way. It's going to be hard because the old me is going to want to pop in, but I'm going to try to show you a different perspective on this perhaps. So it is a significantly more difficult section, but it is also, if you did really well on the quiz that you just got back, then you're probably not going to feel too much of a burn. It's really just if you can solve equations and then do basic math, then you should be fine. But there's a little bit more to it now that they're inequalities and not equal signs. So this lesson is based off of what you already know how to do. Now we're going to start with something simple like this. So obviously they're no longer going to be equal signs at the beginnings of the problems. There's going to be greater than or equal to, less than, and less than or equal to. Those are our four inequality signs that we're going to see. So I am going to teach this one from a very common sense perspective. And then as we get into the harder problems, I'm going to show you a little bit more of a structured way. And honestly, changing it was inspired by a couple different things. The way I teach it, number one, just that it's been really, really, really hard for a lot of kids in the past, a really hard section. And then also, I wanted my explanation to match the explanation in Delta Math, because you're going to miss some problems. And when you do, you know how it is that Delta Math pops up an explanation. I didn't want the explanation, or if you decide to watch one of the Delta Math help videos, I didn't want it to not match at all. So I'm going to take more of that approach for you to see if it helps. And I figure the section can't get harder. I think that this will be easier, but you guys can let me know. And I might kind of sneak in periodically some hints as to how I've done it in the past. And some of the things I say, you'll probably figure out on your own. But we need to start when we talk about this one by just genuinely understanding what absolute value is. And so if I said to you that I'm thinking of a number X, and I want you to tell me all of the numbers that X could be such that the number that I'm thinking of has an absolute value of at least 5. The only way in the world to introduce this and teach it and make it make sense is to draw a number line and to talk about the real core definition of what absolute value means. So in the center of my number line, I'm going to place the number 0. Because, absolute value is really founded on 0, distance from 0 specifically. So if I said to you, I'm thinking of a number whose absolute value is at least 5, what could my number be? So let's start with that. If I did -5 and 5, like Mari said, are those solutions to this problem? They are. And the reason they are is because that problem specifically says or equal to. So we can start by acknowledging that this is a solution, and so is this. However, these are not equations, they're inequalities. So what else could my number be? Could 6 be a solution? It could be. What's the absolute value of 6? And 6 is greater than or equal to 5. So 6 is a solution also. What about 7? What about 6.2? What about a million, right? Those are all solutions. I think you agree. So what happens is as we sit and we talk about what numbers could be solutions, we realize anything to the right of 5 is also a solution. So my graph And graphing is a huge part now. We don't graph equations because really it's pretty silly. That's just two dots, right? But with inequalities, the understanding of this is really completely founded on graphing. What else could my number have been? Anything to the left of -5, right? And if you don't buy it, I mean, think about like this green dot here, like -7, for example. If you put -7 right in here where this arrow is pointing, what's the absolute value of -7? And 7 is greater than or equal to 5. That is true. So what we figure out, like Irene said, is not only are all the numbers to the right of 5 solutions to this math problem, but so too are all the numbers to the left of -5. So our graph for this one winds up looking like this. Now, the way we actually mathematically answer this question is going to be a little bit different. Like I can't, if I just said name one side of it, you could. One side or the other, you could. But when we name them together as a package deal like this, we have to use a really important word. And today would be a great day, like right now, for you to get this word into your notes. It's a very simple word, and it's or. This word plays a critical role in our success here because what we understand is that I could be in the package of numbers that's to the right of 5. Or I could be in the package of numbers that's to the left of -5, but there's no way to be in both places at the same time. So when we answer this math question, I'm going to write this in yellow now. The answer to this math problem is x is less than or equal to -5, or x is greater than or equal to +5. In the yellow box is the solution for the problem. No longer are our solutions for the next week or so going to be little discrete numbers, cute little answers like x equals 2 and x equals 10/3. Like our answers now are going to be infinitely large packages of numbers because infinitely large sets of numbers can make inequalities true. Does that make any sense at all? Let's switch the perspective. Okay, let's do a different math problem. Let's do the absolute value of x is less than 4. And again, the only way in the world for this to come to life is on a number line. So we're all going to sketch just a simple number line. And again, for now, we're going to place 0 in the center. After we survive these first couple of introductory examples, we don't have to keep putting 0. Right now, it works as an instructor because 0 is central. And we're seeing symmetry. We're seeing things that are equally far away on the right and the left. And that's why 0 is good for us to see. But as our answers start to move around, 0 is something we kind of just say bye-bye to. What are some solutions? I'll take anything. Let me ask you this. Is 4 a solution? Not quite, is it? And I understand that because if I put 4 right there where that green arrow is pointing, it's the absolute value of 4, which is 4. And 4 is not less than himself, right? And so to express that we got really, really close, but that 4 doesn't work, we have to go on the number line and put a circle that we keep open. Do you remember this? Nice. So an open circle does the job of telling us that that point is what we call a boundary. It's not a solution, but by leaving it open, we say that there's some stuff that starts happening here. Just don't count this guy. What about -4? And I think we would agree that the explanation is going to be the same, right? If you go to where the green arrow is and you put -4, now instead of the absolute value of 4, it's the absolute value of -4, which again is 4. And 4 is not less than himself. Therefore, I can express again over here at -4 that you're a boundary. You're where some cool stuff starts happening, but you're not in the club. If you get an open circle, you're not in. The question becomes now, these are not equations, so where are the other answers? Could you give me another one? What'd you say? To the left of 4. So like over here? No, I'm curious. Someone pick a number right now and tell me if it works. Go ahead. Did you say 3? I like 3. 3 works just fine because if I put 3 again where the green arrow is pointing, it says the absolute value of 3, which is 3. And 3 is in fact less than 4. So if I was going to make some more solutions, I could say 3. You're good. You're in the club. What else? -2 is just fine. What else? Anything in between them is a great way to say that. Good. So what we see here is an entirely different format of graph. That last one, you're going to hear me use these words a lot, like hundreds of times in the coming weeks. That last graph is what I call a splitter. It's not a mathematical term. It's just how I've chosen for decades to communicate with my students the physical sort of vibe or structure of that graph. You see that it has to split outwards because to satisfy the problem, we need to find numbers that are far away from the center of the problem. This next graph, the points that work are not being split and forced away from the center. They're actually being gravitationally sucked inwards like this. Any point in between -4 and 4 is the solution. This graph cannot have arrowheads on it. It does not go infinitely far to the left or to the right, because if you leave the safe haven of -4 to 4, the absolute value of your number gets too big. I call these ones squishers. You do not have to, but you'll hear me say it a lot, so I figure you might as well know what I'm talking about when I say it. So as far as I'm concerned, for this first few days of absolute value equations until they get weird, we're going to see splitters and we're going to see squishers. Okay. And that decision as to which one is it is predicated entirely on the direction of the inequality sign, as you'll see. So the question becomes, well, how do I write that? In plain English, I would just write down what Irene said. But we can't, as you know, in math, we don't answer questions often with plain English. Math has its own dumb language all of its own. If I wanted to answer in plain English, I'd say, oh, it's just anything between -4 and 4. The way we say it in mathematics is like this. We say -4 is less than x is less than 4. That is how we write squishers. No ors, no ands. It's just a thing. And that's a really cool statement right there. If you think about it, that's actually 2 statements built into one. It's pretty rad. If you take the one that I've underlined in purple, read that to me. What does it say? Read it the other way, please. It says x is greater than -4. When we read inequalities backwards, right, we have to say the inequality sign backwards. And you can actually see x is greater than 4 as the wave starts to crash over to the east. You can see us saying x has to be bigger than the left boundary. But then we have this one that I'm underlining in red, and it says x is less than 4. And you can actually see that force pushing in. And as those 2 forces collide, each boundary says, you're not going outside me. And as they force themselves inwards, they collectively form a pool of solutions in the center where everybody is happy. So that's what we're going to be working with for the next at least week, probably more. This one takes a while, our squishers and splitters. Now, I'm going to try really hard as we get into the actual examples for the day to teach you exactly the way that I saw on Delta Math. And you're my first time. I've never taught it this way before. And I'll probably show you a little bit of each, but I'm going to try to stick more with this other method to teach you. So here's our actual first example. Just I'm going to throw this out because it's in my it's in my DNA. I can't not ask this question. Does anyone know whether this one's going to be a squisher or a splitter? It's going to be a splitter, right? Let's take a look at it, and I'm going to show you the actual best mathematical way to make this as simple as I possibly can. Step one is to get the absolute value by itself, which it already is. So we don't have to worry about that. Step two is to change that greater than sign into an equal sign. And now we're right back to where we were last week. You're back in your comfort zone. It's an equation. And what do we do with an absolute value equation like this? And right. Remember, we're back to Splitsville now. So we're just back to last week's lesson now. We're going to find our boundaries is what we're actually going for here. So if I take off the absolute value and write my first equation, I get x plus 4 equals regular 13. If I take off the absolute value and write my second equation, I get x plus 4 equals negative 13. Now, what we're going to do is we're going to solve these. And if this were last week's quiz, we would be done after we solve. But all we're looking for, again, are the boundaries. The boundaries are just part of the answer here. So if I solve the red equation, I get x equals 9. And if I solve the purple equation, I get x equals negative 17. So it's at this point in the lesson where I'm going to stop putting 0 on the number line. 0 won't serve as much of a purpose anymore as he did for those first 7 or 8 minutes. I actually don't really give a rip where 0 is anymore. What I do care about is where are my boundaries? And so I'm going to draw a number line. And I'm going to mark off my boundaries first. Make sure that regardless of what order you write your equations in, that you always put the red and purple numbers in the correct places. You might think, could someone actually do this on a number line? Are there humans capable of this? And the answer is yes. I've seen it happen quite a bit, actually. So remember, don't be a knucklehead. When you put numbers on the number line, pay attention to where they ought to be relative to each other, okay? Negative 17 is obviously to the left of positive 9. So far, so good. So what we don't know right now is, does the graph shade in towards the middle or does the graph shade towards the outside? And to do this, we're simply going to test a point from all 3 regions. And I would hope that you do see that there are 3 regions. There's the yellow region. There is the purple region. And there is the red region. We would agree, right? Those boundaries have broken the number line into 3 partitions for us. So let's begin by testing a number that's to the left in the yellow. Could you give me an example of a number that's left of negative 17? Negative 20 is what I was going to say first, and negative 18 would work just as fine. Now, what we're going to do is we're going to go back up to the problem up here, this one that I'm drawing a yellow box around, and we're going to test a number. If it's true, then we know that every other number in that region will also be true. So if I check negative 20 and Mari wants to check negative 18 and Kennedy wants to check negative 64, we're all testing points in the region in question. So if I test negative 20 and I put it in where that little yellow arrow is pointing, that is the absolute value of negative 20 plus 4. What is negative 20 plus 4? Negative 16. And what's the absolute value of negative 16? And 16 is greater than 13. Therefore, we can rest assured that all of the numbers that are to the left of negative 17 are in fact solutions. If you test one point in a region and it works, every other point in that region will also work. The boundary ensures that. While we're here quickly, what do you think the boundaries are going to have? Open circles or colored in circles? Open, because we don't see an or equal to in this problem. So we know that the boundaries, while they are pretty cool, they don't themselves work. So while we're here, we can set up open circles that are negative 17 and are positive 9. Now let's test a point in the purple region. Can someone give me a point, a number in the purple region? The easiest one in the world would be what? In the purple region? That's okay. I was thinking of 0. I mean, 0 is pretty sweet, right? If you put 0 over where that yellow arrow is pointing, what is 0 plus 4? 4. And what's the absolute value of 4? And 4 is not greater than 13. If any point in a region is not true, then every other point in the region is also not true. Finally, let's test a point to the right of 9, like 11. If we put 11 where the yellow arrow is, what's 11 plus 4? 11 plus 4 is 15. And 15 has an absolute value of 15, and 15 is greater than 13. Therefore, 15 works, so does every other point on this side. And just like you guys surmised when I asked you the question 3 minutes ago, it is a splitter, and its graph looks like that. Now, to write the solution. How would I write the solution for this? Because that's just the graph. I need the actual math answer now. What would I write for a solution? I would refer you back to your first example from your notes if you want to know. Perfect. X is less than negative 17, or you must use the word or. X is greater than 9. So your answers now are not numbers. Your answers are infinitely large sets of numbers written as inequalities. Okay. Let's do another one. Did that feel okay? Like I've never, ever in my life given that explanation before, so I hope that made sense. Create 3 regions, test, test, test. Good. Okay, let's go again. The absolute value of x minus 8 is no more than 12. Again, in your heart, based on what you've absorbed to this point, is it a splitter or a squisher? It's probably going to be a squisher. This matches example number 2 at the top, the beginning of our warm-up problems, because that less than is going to pull the numbers towards 0, towards the center. So first, let's establish our boundaries. So we're going to replace with an equal sign. And then if you don't want to show that, that's okay. You just want to know right from here. Let's just write our 2 equations. X minus 8, maybe it equals 12. Or x minus 8, maybe you equal negative 12. And again, we're not finding the answers. That's critical. We're finding the boundaries, right? They were the answers last week. Now they're just the start. For the red one, what is the solution or the boundary? 20. And for the purple one? Negative 4. Adding 8 to both sides gives us those. So we're going to draw a number line now. And those boundaries are going to split our number line up into 3 regions. I don't care about 0. Remember, I'm just going to put the numbers in a sensible order. Negative 4 goes here. Obviously, 20 goes here. Don't worry about perfect spacing. That's the trouble with 0. 0 will cause you to get like OCD about, measuring everything out. Just get your boundaries is all we need. So we have 3 regions. I'll just number them for you, region 1, region 2, and region 3. Let's test a point from region 1. Can someone give me a number that's in region 1? Negative 5, perfect example. If you put negative 5 up here where the yellow arrow is pointing, what is negative 5 minus 8? What is the absolute value of negative 13? Is 13 less than or equal to 12? Nope. So if negative 5 is a load of baloney, so is every other point in region 1. Region 1 does not get shaded. Got it? If one point is a lie, every point in that section is a lie. And it will be a closed circle. I agree. And that's something you can fill in right away. I haven't set a good example of that, but if you want to do your boundary circles straight away, great idea. So like right now, we know because of the or equal to in the problem that our boundaries are going to be colored in. That, remember, implies that the boundaries will work. So let's test a number in region 2. Can someone give me a number in region 2? 0 is always going to be the one I like to use. Like, why not? And so if you put 0 where the yellow arrow is pointing, what's 0 minus 8? Negative 8, whose absolute value is 8. And 8, last I checked, is less than or equal to 12. Therefore, if 0 works, so too then does every point inside like this. And then we kind of know this is a foregone conclusion, but to make this official, let's just verify. There will be times coming down the pike later where you actually can have multiple regions that work, which is weird, but not today, not tomorrow, not yet. Okay. But let's just to seal the deal. We know that region 3 is going to be a fail, right? But let's test it. Give me a number in region 3. 21 is perfect. If you put 21 up here where the yellow arrow is pointing, what's 21 minus 8? What'd you say? 13. And what's the absolute value of 13? And again, 13, last I checked, is not less than or equal to 12. Therefore, all fails. If one fails, all fail. How would I write the solution then to this problem? Remember, this is just the graph. What is the solution? -4 is less than or equal to x is less than or equal to 20. Always remember when you write squisher solutions like this that you just have Pac-Mans that are both waka-wakaing to the east. Can you see both Pac-Mans waka-wakaing to the right? So like they're not, you don't want your inequalities coming in. You don't want dueling Pac-Mans, and you don't want like opposing Pac-Mans. Your Pac-Mans are going to follow each other to the east. That's what a squisher should look like. Okay, let's go again. 5 times the absolute value of 7 minus x plus 6 is less than 16. Are you predicting a squisher or a splitter? Squisher? Let's see what happens. What's step 1? We haven't had to worry about it yet. Good listening. Good job. Get the absolute value by itself. If you don't get that memo, you cannot pass the next test. It's impossible. The highest grade you could get is like a 16%. So I'm going to say that again, what Kane said. You have to get the absolute value by itself. It was that way on the last test, and it's that way on this test. So basic algebra tells us that we should take that +6 and remove it by making it a -6. Remember that this 5 with the red check mark and this 6 do not go together, right? They are not related. They don't get to interact. Algebra says to first subtract 6. That leaves us with 5 times the thing we're trying to get by itself is less than 16 minus 6 is 10. Next step. Divide by 5. Now we can get rid of that 5, and we're left with the absolute value of 7 minus x is less than 2. This is the crossroads. Okay, just like with equations, we've made it to the part where now we begin doing the actual problem. So we're going to split it into 2 to find our boundaries. Our first equation is going to say 7 minus x equals 2. Our second equation is going to say 7 minus x equals -2. Some quick basic algebra on the red one. I would move the x to the right and move the 2 to the left, giving me x equals 5. On the purple equation, I would do the same exact thing. I would move the x to the right and add 2 to the left, giving me x equals 9. So we've got our boundaries. Are they going to be open or closed circles? Open. There is no equals with my symbol, so I'm just going to know that the boundaries don't count. So let's mark them while we're here. We're going to put 5 on the left, and we're going to put 9 on the right. And we are going to go ahead and just open those boundaries up like this. And again, if we go with what your gut told you from the very beginning, that it's going to be a squisher, you already pretty much know what the graph is going to look like. But let's test quickly points from each region. If you test for me a point from region 1, give me a number from region 1. 2's fine. If you put 2 up here where the yellow arrow is pointing down, what is 7 minus 2? The absolute value of 5 is 5. Last I checked, 5 is not less than 2, proving that region 1 is a fail. Let's test a point from region 2. 6 is wonderful. If you put 6 where the yellow arrow is, what's 7 minus 6? The absolute value of 1 is 1. Last I checked, 1 is less than 2. Remember, if 1 point is in, then all points in the region are in. So we're going to shade in here. And just to make it official, let's prove that region 3 is an F, right? Not going to work. But if you test a point out there to the right of 9, like say 10, 10 would be the obvious choice. 7 minus 10 is negative 3, absolute value of which is 3. And again, 3 is not less than 2. Therefore, that's the graph. What's the solution going to look like for us? Again, this is not the answer. That's part of it, but the answer is not yet written. What would it say? Yep. And it just rolls off the tongue. You just say it like this: 5 is less than X is less than 9. Boom, just like that. You don't even have to say which is. You can just let it flow left to right. 5 is less than X is less than 9. Piece of cake. Okay. One more. Negative 3 times the absolute value of 10 minus 2x minus 6. I meant to put plus 6, my bad, is less than or equal to 0. Are you thinking squisher or splitter? Let's see. We can't really make any judgments yet, but you probably want to think that it's a squisher at this point, just because there's a less than, but watch out. There's a little bit of a trap. So almost done, okay? Basic algebra, again, at the intro is to get rid of a 6 first. So we're left with negative 3 times the thing we're trying to get by itself is less than or equal to negative 6. Next step. Right, which is going to give me 10. The absolute value of 10 minus 2x is what? Good catch. Good. And that's where you can really easily lose people, especially people that have dozed off. We're getting far enough into the lesson now where the human brain tends to just go into like zombie mode. You remember back in the day, we learned, for some of us a longer time ago than others, that when we divide in an inequality by a negative, we have to take our inequality sign and switch it. So something that maybe earlier on looked like a less than problem is actually a greater than problem. And it's here that we build our two equations, find our boundaries, find our solution set. Would you like to say now whether you think it's a splitter or a squisher? It is a splitter. And it looked like a squisher from the beginning because it had the less than sign. And if you haven't pieced that together yet, the less than implies squish and the greater than implies split. But we now see its true identity. It was hiding from us at the beginning. But now we're like, I see you. I see who you really are. You're a greater than problem. So let's make our boundaries. Everything that came before this is sort of dead to me now. Okay, I'm going to work on this. I teach my lessons with the assumption that you're not going to make any mistakes going from here to here or here to here. If you're making mistakes there, we just need to sit down and work together a little bit and work out all those kinks, because I don't want to go back and deal with these more complex looking ones. I like the clean one, and that's the one I want to talk about. So my two equations are going to be stuff inside the absolute value equals regular 2, and the other one is stuff inside the absolute value equals negative 2. What's my red solution going to be? You can manipulate equations like this very quickly in your head. The answer is 4. You move the 2x over to the right side, you pull the 2 back across to the left side, and you just see it happening. 2x, 8 divide x equals 4. So one of our boundaries is at 4. How about the solution to the purple equation? Yep, again, good work. You pull the 2x, make it positive 2x, add the 2, make it 12, divide by 2, x equals 6. Algebra 101 right there. Our theory, having pieced the logic of this together, is that it's going to be a split. But let's start with a number line and let's get our boundaries on there. By the way, you do not have to graph in your assignment today. Just the graph for me is a very non-negotiably critical thing to understanding what's going on. So you'll be doing delta math, and when you type them in, you'll just be typing in the algebra answer, not the graph. On my test, you'll have to do the graph. So 4 is a boundary and 6 is a boundary. And what's our theory? Oh, they're closed. I agree with you. Good. Bless you. Because of the or equal to, we're going to color in our boundary circles to say, hey, those work. They count. I mean, it's either going to be a splitter or a squisher, right? So if you wanted to save a little bit of time, let's test a point in between 4 and 6, and we're assuming it's going to be a fail. But if not, then we'll be like, whoa, where did our logic fail us here? So let's test the obvious choice, 5, because 5 is pretty smack dab in between 4 and 6, right? So if you put it in here, you go 10 minus, what's 2 times 5? What's 10 minus 10? 0, and the absolute value of 0 is 0, and 0 is not greater than or equal to 2. So we can rest assured that everything in the center is in fact a fail. If you wanted to feel better about it, check a number in regions 1 and 3. And to make this lesson complete, I feel like I should. So a point to the left of 4, a good example would be 3, right? Simple pimple. So if you do 10 minus 2 times 3 is 6, what's 10 minus 6? The absolute value of 4 is 4, and you're like, hey, 4 is greater than or equal to 2. I'm going to go ahead and shade region 1. And then to really seal the deal and make it officially official, let's test a point in region 3. Logical choice would be 7. Try to stay as close to the boundaries as possible, right? You could test 50 if you wanted to, I don't care. But 7's pretty logical. What's 2 times 7? What's 10 minus 14? -4. And the absolute value of -4 is 4. And again, 4 is greater than or equal to 2. Therefore, that's a dub. So boom, over there. Like that. How would we write this out? How would I type this into the old Delta math? What do I type in? X is less than or equal to 4. Or, that is critical, or X is greater than or equal to 6. So that concludes the lesson. Suffice it to say, tomorrow will be a work day. So that took a little longer, but it always does. So that's how you do splitters and squishers. Tomorrow we will work. I'll go ahead and pull the assignment off of the computer so that it's not even tempting. And then tomorrow we'll just get here and get right to work. Sound like a deal? All right.